So thank you all for coming and joining us here this afternoon. If you have questions along the way to clarify any of the points, let us know. We'll also have, I hope, a lot of time at the end for discussion and feedback and to look at some of these points in greater detail. So the question that we started with is the question that an academic would always start with, which is, are these alternatives actually available and affordable, and what would the downstream impacts be of pursuing them? So the first thing we looked at is what are the alternatives that we were going to focus on, and so we chose to focus on two principal heating technologies, ground source heat pumps and air source heat pumps. And to give you a sense of how this technology has been growing, this just shows the cumulative shipments of ground source heat pumps in the United States over the last decade or so. 2009 is simply the last year that the DOE produced this data set. So you can see that this technology has been growing and has, over the last decade, really moved beyond niche technology and is getting to be quite widely deployed. So we started with this question of the pipeline and the areas that it was going to serve, and what we decided was to try and create a case study. We wanted to look at what would the real-world implications be of trying to look at alternative design choices beyond using natural gas. In the area that the pipeline is to be feeding, we found Village Solars. This was in the expansion of the Village Circle. We picked it in part because of its geographic location and in part because they had already produced enough information in public for us to know the design choices that they were going to make, the sizes of the buildings, and all of the information that we needed. So it's a big development. All told, it's looking to add 312 new units to the existing system, a fairly dense development. These units here, these collections of boxes, these are going to be the new pieces that are added on. And what you can see is they often come in these little discrete blocks. So what we decided was to focus in on just one set of those units, the 12-unit block of apartments here, 3 stories tall. As we go across, it was the most commonly repeated unit in the Village Solars design. And so all the numbers that we're going to look at are for those 12-unit blocks, and then they're just repeated over and over again. So one of the things that we found as we began to look at this more, and as we began to meet with the actual developer and architect for the site, who's with us here today, was that there's actually quite a lot going on at Village Solars that already is trying to look at the sustainability of the site. So just 2 quick examples here to give you a sense. In the design of the overall floor plan, they left this pathway here for this community trail that would cut across the site and connect up ultimately to walking trails in the area. They were looking at the energy of these buildings in a number of different ways. They were looking to maximize daylighting, so they've designed the overhangs of the building to maximize light in the wintertime and to minimize the solar gain in the summer. And they have glazing on the front and back to maximize passive pass-through ventilation. And so these buildings were already looking at quite a few of the kinds of technologies and design choices that we would have been advocating anyway. Our methodology, we picked the DOE's prescriptive methodology. Every time the building code changes, the DOE uses this same methodology to look at what are the energy costs and energy savings that you would get from the new energy code. So this was looking at the change from the 2009 International Energy Conservation Code to the 2012. We picked this methodology for 2 reasons. One is it's a common methodology that would allow us to baseline our study against a known set of numbers, but also it gives us a common set of costs, and we use this DOE building community, building component cost community. So all of the costs for things like insulation, for air sealing, everything that we used except for the heat pumps themselves came from this DOE study and DOE database. The cost for the heat pumps themselves, we looked at local costs from local developers because those can vary more widely. So what we started with was the question, okay, we have right now, at the time these were put forward, the 2009 building code. when we started this work last year, it looked likely that New York was going to be adopting the 2012 Energy Code. And so the first thing we looked at was what would the implications be of simply adopting the new energy code. So in terms of its heating and cooling loads, the two biggest changes from the 2009 code to the 2012 were small improvements to the window systems and a fairly substantial reduction in the air infiltration standard. There was a much tighter standard and required that it actually be verified with a blower door. The New York looks like it will actually probably be skipping over the 2012 code, but that's fine because we didn't really end up using it for much beyond the way of comparison. We wanted to see what would a smarter building look like. So we proposed what we called the Smarter Energy Building, and as our goal, we wanted to know what would you need to do to the building design to achieve a 20% improvement over the existing, over the 2012 code. So 20% is a pretty sort of common number to look for an initial savings. It came philosophically from two places that are fairly common. LEED standards, 20% reductions off of their code is that first sort of big LEED jump. And 20% energy savings is what Governor Cuomo has required for all state-owned buildings by the end of this decade. So it seemed like a reasonable target for us. And what we found is that you can make this 20% reduction without radical changes to the envelope. So for instance, it's 2 sheets of insulation on the outside rather than 1, so you double the R value for the wall. You have improved insulation on the storage tanks, and the biggest single change was the introduction of heat recovery vehicles to the ventilation systems. So when we looked at those buildings and we modeled out that set of 12-unit apartments, what we found was here's our usage for the current code. The blue is the space heating. The red was the domestic hot water requirements. As we moved from there to the new code, we got about a 27% reduction, much of that from the improved air sealing. And as you moved from the new code to our smarter building, then a further 22% reduction. So all told, we were looking at an envelope that was using about half as much energy as the one that was built just to code, so about a 46% reduction. And the more energy that you can save in the envelope, that's going to have big economic gains for us down the road, because it means that the alternative systems, the ground or air source heat pumps that we're going to put in, can be smaller because they're meeting a smaller load, and they can also then be displacing this much larger natural gas system that would have to go into the original building system. Now, 46% reductions, that seems like an awful lot to be able to get out of a commercial building, out of a multi-family home. Wanted to give you a sense that that's not actually all that aggressive when you look at what can really be done with some of these buildings. It's one of my favorite pictures. This is a retrofit from Germany. This is before the retrofit, an infrared image showing the wall cavity. This is after the retrofit. And you can see that even in this retrofit, which is much harder than new construction, they achieved almost a 90% reduction in the total energy consumption of the building. So very dramatic. So 46% is certainly a big improvement, but it's not as big as some of the buildings that we're going to look at later on. As I mentioned, the existing Village Solars is being built above code, so the wall systems are have a higher R value than the wall systems. The windows are better than this sort of baseline windows. What we know of the construction so far, we were able to estimate that it's probably about 16% below the existing code. Our building would be another 30% reduction beyond what they have proposed. And again, one of the largest components to this is the assumption that we have introduced heat recovery vehicles into the ventilation so that all of that energy you've put into heating the air doesn't get blown right back out, and you can recover some of that. So the heating technologies we looked at, as I said, they were ground and air source heat pumps. These are mature technologies that have advanced dramatically in the last decade in terms of their technology. So ground source heat pumps, they use the earth as a reservoir for heat in the winter and as a sink to dump heat into in the summer. They use familiar refrigeration technologies to take that heat that you're pulling out of the ground at 50 degrees and uprate that to around 110 degrees. So these can supply up to 100% of the building energy load depending on the design. So these are incredibly efficient because what you're using now is energy. Instead of to heat the building directly, you're using energy to pump fluid into the ground through these closed loops here, and you're using that to extract energy for free from the ground. And so when you look at the efficiency, for every unit of energy you put in, you're getting up to 3 units of energy back as heat energy. So when you look at the efficiencies, the efficiency of the system is 300%. So for every unit you put in, you're getting 3 back. You can compare this to a typical natural gas system, which may be 95% efficient, which means 95% of the heat energy in the natural gas that you put in actually shows up as usable heat energy in the building. So these systems are going to give you much lower energy uses, and that's where you're going to recoup some of the additional cost. These ground loops can either be vertical bores, they can be drilled into the ground depending on the geology of your site. Some of the typical commercial wells that we're going to loop at are between 300 and 400 feet deep, or they can be horizontally trenched if you have an appropriate soil geometry, and then you are using long trenches rather than deep wells. Air source heat pumps, very similar technology. They use very much the same refrigeration idea. The only big difference is instead of using the ground as your heat exchanger, you're now using the air itself outside. So instead of trying to extract heat from the ground at 50 degrees or reject heat to the ground at 50 degrees, you're now trying to extract heat from air that's much colder or reject it to air that's much hotter in the summer. So instead of 300% efficiencies, they have averages around 200% over the course of the heating season.
So my understanding is with the COPs for the ground source heat pumps, they don't usually take into consideration electricity used for the pumps themselves, pumping the fluid. Did you take that into consideration, or?
We have looked at that. The 300% efficiencies are pretty close to the overall efficiency of the entire system. We've got monitoring data for a number of the residential scale pieces. Yeah. For air source heat pumps, newer models can remain efficient down to can remain operational down to -13. As you go below the very low temperatures, they effectively kick over into simple electric resistive heating units, which is again why they have lower efficiencies overall than the ground source. Their principal advantage is there's no loop field, there's no drilling, there's no trenching for the system, so they have lower upfront costs, so they have smaller installation costs, and they have less savings, so higher operational costs.
Brice?
Yeah.
This is a kindergarten question for others, I'll learn it later, but how do you get efficiencies over 100%? What do you mean by 200 or 300%?
So you're putting in a unit of energy to run the pumps, to run the fans, to run the system. So that's the energy you're putting in. But that's not the energy that's then going directly into heating your home. You're using that to extract heat from another source. For the air source, it's from the air. For the ground source, it's from the ground. So the energy that comes back to you is larger than the energy that you're putting out to run the pumps and run the fans and compressors and all the like. So if you look at how much heat is delivered into the home compared to the amount of energy that you're putting in to run the fans and pumps, you're getting, in the case of air source, twice as much energy into the home as you're putting in to run the fans. For a ground source, it's a factor of 3. So the energy is coming from the either air or ground, so it's not free, but you're simply extracting that renewable heating energy that can then be replenished by the sun and other natural processes. And it's when you combine these highly efficient heating systems with the better envelope that you see the really dramatic reductions in overall building energy use. So here's our natural gas business as usual building. This was the building built to the existing building code where you've done nothing more than the minimum. If you look at our smarter building with ground source heat pumps, you get about an 80% reduction. With air source, you get about a 75% reduction. So what our question was is, what does the economics of this look like? So the ground or air source heat pumps are more expensive than a simple natural gas unit. So how does the reduced energy costs and those different upfront costs, how does that all wash out in the end? So we looked at sort of what these premiums are. So when you add up the cost for the insulation, for the air sealing, the heat recovery, the new ground or air source heat pumps, came out to about $50,000 to $60,000 for that unit block of 12 apartments. So that means it's around $4,000 to $5,000 per apartment that we're looking at as the cost premium for these smarter envelopes and for these more efficient heating systems. This you can compare to things like your granite countertops and other kinds of items you might see put into an apartment. And later on, we're going to talk about some of the ways that this can be reduced, both through some assumptions we are not taking into account, as well as some changes to the whole design process that we can employ. So the cost premium, if you look at the construction costs of these kind of buildings, this is only the construction cost, so not the cost of the land and the other associated elements. We're talking about maybe a 2.5% to 3% increase in the overall cost of the building from adding these much smarter energy systems. But we, of course, look at this not as simply a cost, right, that developers aren't doing this out of the goodness of their hearts, right? They can do this because they can also make money on the investment. They can treat that 2 to 3% increment in the cost as a way to invest and receive a return. So we looked at 12% pre-tax rate of return. We'll talk about the sensitivity of that number if you're looking for a higher rate of return. We picked 5 years as the payback time, so that's when you're going to have achieved your 12% rate of return. And we designed the system so that it would be cash flow positive within the 18 months after you end construction. So the revenue streams to the developer would come from a number of places depending on how it was that you would have structured the heating bill to begin with. In many multifamily homes, you have a single natural gas input, and you are then passing on the cost of heat to the tenants through the rent. So what you would have is here you'd be displacing that central natural gas, going to electric heating for ground or air source heat pumps, and you'd have adjustments in the rent that you would have. In other cases, if those costs are passed directly along to the tenant, then those would come back through this rent premium that we're going to talk about. So we looked at operating savings, those big reductions in the overall cost of energy to the building. If you look out over a 30-year lifetime, there's an awful lot of savings that you recoup, somewhere between $40,000 and $87,000. So this is in your total energy savings. So when you look at those energy savings, you distribute them between the tenants and the owners as you will. What we found was that you would have to charge a rent premium on top of those energy savings in order to make that 12% rate of return. And the rent premiums are fairly insensitive to the technology. So the air source heat pump would require about a $46 rent premium, the ground source a $47 rent premium. The reasons they're very close is simply that the air source saves you less money over time, but it costs you less money up front because you don't have the cost for the drilling or trenching. If you want to move from a 12% rate of return to something closer to 16% rate of return, these don't increase very much. They increase by only $2 to $4 a month. So it's a fairly insensitive increase if you want to have higher rates of return. Now these apartments are designed to be market rate, so they are going to be rented, we assumed, for around $1,000 a month per unit. So we came out with a rent premium of around 4.5%, between 4.5% and 5%. So these rent premiums are modest compared to what we find for other commercial buildings that have these green features. And we'll talk about those in a sec. Give you a sense, though, of what that cash flow looks like. If you are the developer and you hold on to these investments past year 5 and continue to charge that rent premium, you can see that your cash flows grow quite quickly. Here is your air or ground source heat pumps. We assume that you financed this over 15 years. So that's why there's this knee here in the financing. So we have 15-year financing. We assumed 6.5% as the finance rate. And what we found was that at year 5, this is your 12% rate of return, either the natural gas or the air or ground source heat pumps. As you hold on to these investments and continue to recoup those rent premiums and those energy savings, your cash stream increases quite quickly with the air and ground source heat pumps. So the longer you hold these, the more rapidly, very rapidly, do you have higher rates of return. The other option here, of course, is that if you're looking to do things like control the rent premiums to have lower income people more able to afford these technologies. We'll talk about how it doesn't necessarily have to cost these premiums. These are premiums you pay generally when you're tacking on at the end of a design. But even with this rent premium, at year 5, you've made your 12 to 16%, depending on the premium. There's no reason that you have to continue these rent premiums beyond year 5 and continue to achieve higher and higher rates of return as you go forward. If your goal was to make more affordable housing, you can cut those rent premiums off after a point, and that will help make these apartments more affordable in the long run.
Over a 30-year span, have you made any assumptions about repairs or, in particular, replacements of the air source units?
Well, we were focused on principally on the early parts. As we go out to the ends, we haven't made any assumptions for maintenance on either the gas or the air ground source heat pump units.
I heard that the heat pumps only have a 14-year lifespan on them. That's a good question.
The air source or ground source?
The ground source. I heard they only have a 14-year lifespan. Do you know how true that is?
It's not certainly what I've seen, and the well fields themselves are warrantied out for decades. I mean, the well fields are assumed to last for 40 years, depending on how they're put in and what exactly, whether you have the vertical or the horizontal.
Yeah, with the compressor life, exactly, for any compressor, be it for a refrigerator or a heat pump, it's 14 years. They don't make one that lasts longer. I mean,
well, a well-designed ground source heat pump would probably be fairly maintenance-free for 20 years or more.
oh yeah?
The most common repairs probably contactors. And the one thing to keep in mind is, depending on the system, if it's a package system, it's all put together in a factory environment. So they've got, the scale is perfect, everything's a lot easier than when we're doing things in the field and, did someone bring nitrogen or not, and all that kind of stuff. But most of the systems that were installed in the earlier generations still run just fine with minor maintenance. Air source heat pumps different because they're exposed to the elements and you have on-site brazing to do, so they don't perform as well.
And some of the newer air source heat pumps, we have less field data, but the ground source we have quite a lot of field data for. If we kind of summarize our pieces, so the average O&M savings, so if you look at those energy savings for your multifamily home, we're talking about $1,200 to $2,500 per year on average. That rent premium around 4.5% to 5%, and your construction premium of around 2.5% to 3%. These numbers will change slightly depending on how you were going to recoup those heating costs up front, but we've tried to make the most conservative assumptions, and so here we've only allocated about 85% of the energy savings to the actual owner of the facility, with the remainder passed along to the client. So to compare those numbers, we looked at what has been achieved in actual green building that people have looked at. So this is a study that the DOE did last year, looking at a collection of different green buildings. So quite a lot of text on their slide here, but some key numbers to take away. Higher rental rates. So what they found is for LEED buildings, the typical rent premium was between 15% and 17% over conventional buildings. For just Energy Star rated buildings, they were still finding rent premiums of 7% to 8.5%. So the rent premium that we were looking at to make our 12% rate of return was that 4.6 to 4.7% return. So about somewhere in the neighborhood of half to 2/3 of what you can conservatively find from similar typed buildings. That is driven in part by higher occupancy rates because of the lower operations costs of these buildings. They have an occupancy premium. They have a higher sale price at the end of their life, so 10 to 30% premium for LEED buildings, a 6 to 10% sale price premium for Energy Star buildings. And their cost premium overall was found to be around 2%, which was comparable to what we found, 2.5% to 3% for our cost premium. So it does look like these technologies do have a strong economic case, even when you look only over those first few years, as a developer looking out only that first 5 or 6 years. And what we have done here is tried to keep the most conservative elements of our assumptions so that anything that would change would only make our economic picture look better. So to walk you through some of those conservative elements, I'm going to turn over to Melissa now.
Great.